Hi, this is Jeff Coronado on behalf of JCSC, and this is Bridging the Gap. So, Bridging the Gap is a series of structural engineering design tutorials that we have here at our office that are intended to bridge the gap, meaning there is quite a gap between what you are expected to know when you are in school, when you're in college, and to be able to get through college, and what you're actually expected to know when you're in industry. So whether you are just short of graduating from college and you want to aspire to be a structural engineer, or you're in your first couple of years of your structural engineering career, there is this gap that's overwhelming of what you need to know to be able to function in industry. And for those of you that are still in college, as you probably know, it is structural engineering positions are highly competitive. And in fact, most people that graduate from college, let's say with a civil engineering degree, and aspire to be a structural engineer are probably not going to make it. There's just too few spots for the number of graduates. So if you find yourself in that situation where you are that young aspiring structural engineer, or let's say you did get a break and you are able to get in, remember there's a lot of people behind you chomping at the bit, if you will, to be a structural engineer. So if you don't quickly take flight in your career, if you don't progress, you might find yourself getting replaced by kind of like the next generation, if you will, of aspiring structural engineers. So for those of you that are on either side of that graduation line, again, whether you've just graduated or not just graduated, if you've graduated within the last couple of years, or if you are going to be graduating in the next year or two, you will find these tutorials to be very helpful for you to bridge that gap. All right, the title of our tutorial this time is how to calculate the wind effective area for a stud wall. So the question is, when determining the wind pressure on a stud wall, is the effective area of the wall based on the dimensions of the stud or the wall? So is it basically, do you take the effective area for a stud or for an individual stud, or do you look at the wind effective area when you're determining the wind effective area? Do you look at the entire wall as the area that's under consideration? Okay, sure, very valid question. So just as a heads up, notice how the detail here is FW1 underscore 2x4, 2x4. So that means that we're going to cover some topics in this tutorial, but you will likely find other kind of sistering topics that deal with a similar situation to what we're dealing with here, but not covered by this tutorial. They're covered by another tutorial in Bridging the Gap. So on our channel, if you search for FW1s or FW1 underscore 2x4, you might find other topics being covered that are related to this topic, and they might help you as well. So just kind of a hint, you might want to search on our channel for this detail to see if there are related topics as well. Get all you can from the tutorial, meaning don't try to skip around, not listen, fade out. When you do that, you shortchange yourself, right? The purpose of these tutorials is to kind of empower you to become a structural engineer, to think like a structural engineer. So if you just get in here and try to pick off one value, one numerical value, you're shortchanging yourself, because then that means that you're going to constantly have to keep going back to tutorials and tutorials for you to understand what you're doing. And reality is you never did understand what you were doing. You were just kind of picking off a value, right? As opposed to if you listen, digest, and learn what you're being taught, then you're armed to do it yourself. You'll see that very quickly. You won't need tutorials to be able to do your structural engineering work. You'll understand how to think like a structural engineer. And that's what we're trying to do here, is kind of strengthen you to think like a structural engineer. Okay, so we're calculating wind effective area. So we're dealing with wind pressures. When we deal with wind pressures, we have wind pressure. I think fair to say in practice we divide wind pressure into two types of winds. There is wind on the main wind force resisting system, and then there are wind force on your components and claddings. That's how the code divides it. So when we are doing wind pressure on a component or cladding, an element, not the overall structure, not the entire structure, but an assembly within the structure, we need to determine the effective area of that assembly, of that component, of that cladding, in order to calculate the wind pressure that's acting on it. So here the question becomes, how is the wind pressure on that component or that cladding, how is it defined? All right, so in particular, we're looking at a stud wall, right? So we've got a stud wall. Do we take the effective area? Do we take, let's say, the width, right? That was the original question. Do we take the width that we're gonna look at here as the width that's tributary to the stud, or do we take the width that's tributary to the entire wall? All right, let's take a look at this figure here. So let's identify the components. Let's see. So we've got well, let's see. Let's start from the ground up. So what do we have here? Well, all of this down here is your foundation. So this is your footing. All right, above your foundation, here we have a concrete slab on grade. Looks like this is an exterior wall. So here you have whatever, your pavement, whatever's on the outside of your structure. And then here is your stud wall. Remember, kind of the stud wall is kind of what we're focusing on, right? That's the question is, what is the effective area when we are evaluating these studs to make sure that they can resist the wind pressure exerted on them? Okay, components, specifics. Oh, the specifics are irrelevant because, okay, in this illustration, we've got, this is a wall at the foundation level, right? It's your first floor wall. This could be a second floor wall. It could be, the structure can be multi-level. The point is we've got a stud wall. Okay, so let me get rid of what we've got here on the screen so far. So those are the components of what we're seeing. Complete load paths. Yeah, complete load paths, 6 forces. So with that, what I'm trying to get you to think is we've got 6 forces. As structural engineers, what we're good at is being able to follow load paths, being able to chase loads down to the foundation, right? We want to be able to resolve all our forces to get them into the foundation. We want to provide enough meat in the structure to get down to the foundation, to get the forces down to the foundation. For any element, any connection, any component, like I'll always think of the 6 forces that are present on that element, that could be present on the element. Doesn't mean they have to be, but they could be. So I know that maybe if this is new to you, you might think, wow, that's tedious if I have to do that. Trust me, if after you do it for a little while, it becomes so second nature that you almost don't think of it, and you fly by the 6 checks that you need to think of. So let's assume I'm looking at the stud, right? So in this case, the stud is basically what's represented right here. This is the stud. All right, so 6 forces, right? So the first thing that I'm going to think of is, let's say F sub x. Let's call this F sub x. All right, forces that push the stud to the right or to the left. Then I'm going to think of F sub y. All right, forces that push the stud up or down. Then I'm going to think of F sub z. So F sub z, for those of you that are not familiar with this notation, F sub z is represented by a circle with a dot in it. What that means is if you see a circle with a dot in it representing a force, that's a force that's coming out of the page at you. Think of an arrowhead, all right? So it's an arrow coming at you. Whereas if we were to draw a circle with an X through it, that represents a force going into the page. That's like the backside of the arrow. You're seeing the arrow go away from you. So whether you see the circle with a dot in it or a circle with an X in it, that represents a force going in and out of the page. That's F sub z. Then we have what? M sub x. So M sub x, yikes, how do we do that? Right. Well, let me use a different color for that. So M sub x would be a moment about this direction. So literally causing, this would be literally looking at the stud spinning as if the stud, so it would spin in our plane as we look at it here, right? It's like looking at a propeller from the side view. So this would be the stud spinning in the plane or out of the plane of the screen, if you will. That's M sub x. M sub y would be the stud spinning, let's say, in its own, about its own longitudinal axis. All right, so this would be what? Like if this was a screw, somebody comes in from the top and puts a screwdriver into it and starts spinning the screw, that's what this would look like, M sub y. Right? M sub z, yikes, M sub z, how do I illustrate an arrow here that makes it somewhat intuitive as to what we are doing? Let's see if I could just draw around here. So this is M sub z, right? So that would create a spin in the plane of the page right now. So this would be like, let's say, looking at that propeller head on. So we would see the stud spin in this page. Those are our 6 forces. So are all 6 forces present on the stud? No, right? Do we have F sub x? Yes, we have F sub x, that red one. F sub x is caused by wind, what we're looking at right here. So that stud needs to resist a pressure that's, let's say, out of the plane of the wall. This would be out of the plane of the wall, not in the plane of the wall, but out of the plane of the wall. And it's a pressure exerted by wind. Do we have F sub y? Yes, could be, right? That would be an axial load on the stud. That's not what this tutorial is about, but yes, there could be an F sub y. Could there be an F sub z on the wall? Yeah, an F sub z on the wall, on the stud. No, probably no F sub z. There might be an F sub z on the wall assembly. Yes, this wall may be a shear wall, in which case there would be an F sub z. Is there an M sub x, M sub y, and M sub z? No, no moments on this stud. So no induced, I'm sorry, no moments acting on the stud. So we don't have M sub x, M sub y, M sub z. Okay, so we have none of the 3 moments, and we have no F sub z. We're left with just F sub x and F sub y, and we're not covering F sub y in this tutorial. So really what we want to focus on is just F sub x, the force that acts on this stud acting out of the plane of the wall, acting from left to right. Okay, with that, let's clear the screen and let's move on here and look at an elevation of the wall. Okay, so for an elevation, let's see. Let's start off again kind of on the lowest point. So this is, if this is a stud wall assembly, that horizontal element that goes across the bottom, we can either call that a sill plate or a mud sill. I think you'll hear both terms. Here we have studs, right? More than likely, these are going to be spaced at 16 inches on center. And then at the top of the studs, we have two horizontal members. Typically, we'll have two horizontal members, which are referred to as the double top plate. If there's only one, I guess, sure, you can have a single top plate. Pretty unusual to have a single top plate. Probably you might see that in an interior wall. You might see that in a real short wall, real short interior wall. But I think even in short interior walls, I think it's just customary to frame it with a double top plate, not just a single top plate. So there's our double top plate. We need to have some connectors here, sure. Probably we've got some nails. Oops, didn't mean to do a circle, sorry. So we need to have some nails that kind of connect the bottom of the stud to that mud sill, and we need to have nails that connect the top of the stud into that top plate. The stud effective area or wall effective area. So remember, what we're trying to see is if when we are doing our stress check to make sure that the element, in this case the stud, is adequate to resist the wind pressure as calculated in our wind component and cladding expression, what is the effective area that we take? So the question becomes, is the effective area going to be the effective area as if we were looking at a single stud, so the tributary width of the stud times its height, or is it going to be the effective area for the entire wall? Right? Which one of these two represents the effective area that we plug into the equation to determine the component and cladding force? All right, let me see. Can we clear this here? So hopefully at this point, what starts to become evident for you is that if you just listen to the wording, it's the effective area of the element is that we are looking at. The effective area of the element. So that should start to kind of point to you, kind of give you a hint that really what we're after is the effective area for the stud. So it really doesn't matter if we are checking, if we are doing our stress check on the stud, we need to look at the effective area for that stud. Doesn't matter how long the wall is. We want that individual stud to be able to resist that wind pressure, that out of plane wind pressure that it needs to resist. So our effective area is going to be the tributary width, okay, tributary width of this stud. How do we get the tributary width? We don't get it that way. We get our tributary width by getting the dimension from the stud adjacent to it on one side, the stud adjacent to it on the other side, and dividing that dimension by 2. So in essence, it's this area that's shaded in orange. Then we multiply this width by the length, or the height, I should say, of the stud. So it's half of the green dimension times the height of the stud. That gives us the effective area for the stud. If let's say, we were looking at the nails, okay? Now we're doing a component and cladding check on the nails, because we need to transfer that wind pressure, that out of plane wind pressure that exerts on the wall. We need to transfer that, or that's exerted on the studs. We need to get it into the sill plate, right? Remember, we need to be able to chase our loads, right? As structural engineers, we need to be able to chase our load. So the load is going to go, the out of plane force is going to go from the stud into those nails, into that sill plate, into the foundation, or whatever is below that sill plate. But to get that load into the sill plate, it needs to go through the nails. So sure enough, our nails there need to, or whatever our connector is, whether it's nails or plates, whatever our connector is there, we need to be able to transfer that wind pressure from the stud into the sill plate. But now we need to consider, what is the effective area? What is the effective area for the nails? Is it going to be the same effective area as it was for the stud? Even though the nails are transferring the load from the stud into the sill plate, will it be based on the effective area for the stud? The answer is no. We need to look at the effective area for the nails. Well, what's the effective area for the nails? It's going to be this much, right? That's the effective area that that transfers into that these nails need to resist. That's how much of the wind pressure these nails need to resist. On the other hand, the nails up at the top would need to resist this amount of pressure, right? So if I were checking the nails at the top, it would be for the area that I've shaded in magenta. If I were checking the area, the effective area for the nails at the bottom of the stud, it would be for the area that's shaded in light blue. So those areas, those effective areas do not match the effective area for the stud. Each element that you are checking for your component and cladding pressure is going to be based on an individual, a unique effective area for the design of that force. Now there is one other thing, there is one other thing here to keep in mind, and that is, let's go back to the light green dimension. What the code allows us to do, so the theoretically correct tributary width for this effective area, as we said, was this light green dimension. However, what the code also allows us to do is if this dimension, if this dimension, if this dimension is, let me show it like this. If this dimension is less than L over 3, the height of the stud, divided by 3, then what the building code allows us to do is to take that dimension as L over 3. In essence, L over 3 becomes the floor for that dimension. We do not need to take it any less than L over 3. Okay, so for a stud, more than likely, your tributary, your effective area is going to become the length of the stud times the length of the stud over 3. All right, so just kind of a little thing there that the code allows us to do. Okay, and that concludes the discussion on effective areas for wind component and cladding forces. If you found this to be helpful, if you found this tutorial to be helpful, sure appreciate it if you give us a thumbs up at the end of the tutorial. By the way, one thing that I haven't said is I did mention other tutorials that you might find in our channel that will be related to this topic, not exactly on the topic, but certainly related topics to component cladding and designing your elements for the stresses induced by component cladding forces. So you'll find those, as I mentioned earlier, but also if there was anything that was covered in this tutorial that wasn't clear to you, by all means, yeah, by all means, let us know. Leave us a note at the end. Um, if there's any suggestions that you have to make these tutorials more helpful to you, or other topics that perhaps weren't covered in this tutorial, let us know. We'll try to point you in the right direction. If there's another tutorial in the on the channel that we have that would be helpful to you, and if you did find it helpful, sure, would appreciate if you were to subscribe to our channel. And then I believe there's a way to click or something on your, when you subscribe to our channel, that then automatically alerts you to any new tutorials that we put up on our channel. Okay, all right, real good, guys.